Okay, so for today's lesson, I have the video that I'm posting here just in case I'm not in class. I've got a problem. A cart weighing 420 newtons rests on a 23-degree incline. Calculate the component of its weight that presses the cart to the hill. So, with that, we're talking about things that are on ramps. It's just as simple as that. I've got a ramp. The ramp has a 23-degree incline. I've got a cart on the ramp. And its weight, of course, is the same thing as its effective gravity. And it goes straight down no matter what. Even when you're on a ramp, it's got to go straight down. So it wants to know how it's being pressed into the hill. We do still have components to our weight here, to our force. And that's what I want to show you right now. I'm going to actually move what I just wrote over here, mostly because I always forget to do this. And I'm going to draw in the component forces for weight, just like we have component forces for velocity. So in the lesson that we did from last week, we had things like you had your VI that was at an angle, and we had to break that down into VIX and VIY. We're going to do the same sort of thing here, but here's the trick. You want your forces to match the ramp, not the ground. Your math actually will be a lot easier with what's coming up if you'll match it to the ramp, not the ground. So this will be my positive y direction, and I'm making this to the left be my positive x. You'll see why on a later problem. So I make a right triangle where one of these, the one that comes from the box down, is perpendicular to the ground, and then the one that matches, that goes from there to the vector for weight, is perpendicular to the first vector. So in other words, I'm going to call this my FGY and this my FGX. Now it wants to know the part that presses the cart to the hill. That sounds to me like, what is my FGY? Now, for this, the trick is, turns out this angle right here can be used on this triangle right here. I'm going to show you where it goes, and I'll make another video to prove why. But for now, I'll just show you where it goes, so if you don't care about the proof, you just have to remember where it goes. It goes right up here. So, once you have that triangle together, it's just a trig problem. We have FG is equal to 420 newtons. We have our angle 23 degrees here, right angle. We have an FGY. And we have FGX, but I don't really care about that one because it wants to know how it's pressing it into the hill. So this to me looks like that's the adjacent side. So it sounds like I'm going to need a cosine of my angle will equal the adjacent side over the hypotenuse. Or in other words, cosine of 23 degrees equals FGY over 420. Then solve it like an ogre. Move that 420 over by multiplying on both sides. And FGY will equal 420 times the cosine of 23, which, let me get my calculator going. And of course, since we're using trig, make sure you are in degrees. I'll show you on my calculator. If you pull up Desmos, it gives me this negative number. Remember I told you in class, Desmos always defaults to radians. But just come over here, switch it to degrees. And there we go. That's our answer. 386.6. Newtons. So, of your weight, while your weight is pulling you down, a certain amount of your weight is going to pull you forward so that you're rolling down the ramp or sliding down the ramp, depending on what the situation is, if you have wheels or not. But you still have 386 newtons pushing you into the ramp, which, by the way, well, it didn't ask that. That also does mean your normal force does go perpendicular, remember, to the surface you're on. That's a way to get the normal force, and I'm going to show you some problems that will use that. But I just wanted this one to get you ready too for the component forces. So what we're going to do now is we're going to use some of those things that we looked at in the last problem and apply them to a more full problem. I've got a box here on a ramp. I can see what information I'm starting with. And I'm going to show you how to find the acceleration of the box when our angles are not necessarily just laying something on the ground and pushing it across the floor. So, on this problem, we want to do a free body diagram because that's the picture of the situation. And I know that if I put a box on a ramp, first of all, everything has gravity. Absolutely everything. And like with the last problem, we want to make sure everything is parallel or perpendicular to the surface of the ramp itself. So, perpendicular to the ramp is my FGY, and parallel to the ramp is my FGX. Make sure you've got those in there. And I know I didn't drop parallel or perpendicular, but you know what I'm going after. Also, you're on a surface. You have a normal force coming up. And that is really it. Do we have friction? It doesn't say we have friction, so we're going to ignore friction. There's nothing else pushing or pulling it. There's no tension. It's just gravity and support. That's all we've got going on. So, and I personally, I like to put over here to the side somewhere. Whatever direction the box is going to move, I like to make that my positive X direction. And then whatever direction is perpendicular to the surface of the ramp, I make that my positive Y. Alright, so as I look at this, what we're going to have is we're going to have the sum of our forces in the X direction, and I'm going to add together all the forces I can find in the X direction. That equals the mass times the acceleration in the X. The sum of the forces in the Y direction equal all the forces I can find in the Y direction, which equals the mass times the acceleration in the Y. When it asks for the acceleration of the box, I hope you can see it's got to accelerate in the X direction. You're not going to accelerate off the ramp perpendicular to the ramp. So this is the one that I want to focus on. Super conveniently here, especially since we don't have friction, I only see one force that is in the X direction. So that tells me that FGX must equal the mass of the box times the acceleration in the X direction. I know the mass. I don't know my FGX yet. And of course I don't know my AX. That's what I'm trying to find. But FGX will be pretty easy to find because, again, we're going to rely on our trigonometry. Remember I told you in the last problem, the angle of the ramp is the angle that goes up top here. So I've got my 60-degree angle. My FG, remember, is the same thing as mass times the acceleration due to gravity. In other words, it's going to be 5 times 9.8. So, let me pull up my calculator again, just to double check. 5 times 9.8. I know it'll be a little bit less than 50. I'm getting 49 newtons. And it looks like here, I want the quantity that's opposite side of the triangle. That sounds to me like a sine function. will equal FGX over 49. And we're going to solve this like an ogre. Multiply both sides by 49, so you can get rid of it on the right. And I get 49 times the sine of 60. Now for me personally, I don't like to pull out the calculator as much as a lot of you do. I'm going to just put this in here and just pull out the calculator once at the end. So I'm going to substitute that in. I get 49 times the sine of 60 is equal to the mass, which was 5, times the acceleration in the x direction. Divide both sides by 5. And this is what I will put in my calculator. You do have to be a little more careful to make sure that you are putting, especially with fractions involved, that you're putting in the calculator correctly. But beyond that, you're going to be fine. And of course you're using trig, so make sure you are in the proper units. So 49 times the sine of 60, all divided by 5. And that's okay that it didn't divide the 49. They're the same thing. I'll show you here. Times 49. I get the same answer between them, whether the 45 or 49 is in front or down below. Which was, forgot that was not going to show on the screen. 8.49 meters per second squared. So in other words, it's almost going as fast when you're at a 60-degree angle, which again, while the picture didn't make it look steep, 60 degrees is pretty steep. Your acceleration is almost free fall. Because remember, free fall is 9.8 meters per second squared. You go a little slower than that, but you're still going to slide down that ramp pretty dang fast. So I'm going to do one more for you. One more that has friction. And then I want you to use this all on your homework. Alright, one last problem. We have a force that we're going to push a box up a ramp this time. We are going to have some friction involved. So, get your ramp ready. On this one, I'm going to have to draw it in. Got my box. And it says a force of 160 newtons parallel to the inclined plane is required to move. That sounds to me like it's an applied force to push it up the ramp. We know the weight of the box. Now keep in mind, weight is the same thing as Fg. Of course, over on the side here, Fg equals mg, but mass is in kilograms. Force of gravity is in newtons. What they told us was already the weight itself. So I don't have any calculating to do there on this problem. So it's required to move a 200 Newton weight up the inclined plane at a constant velocity. I'm not going to worry about that phrase yet, but I will need to very soon when I start putting my equations together. Find the coefficient of the sliding friction. So we got friction involved, which means friction, of course, fights your applied motion. And I'm going to put over here, mu equals question mark with a box around it, since that's the thing I'm looking for. Find the coefficient of sliding friction if the plane is inclined at 30 degrees. So, once you've got your problem together, you need to draw in some more things. First of all, you always need to break up your gravity component into FGX and FGY. Now here, because I have more forces, this is where I really want to make a big deal. Do you see how you've got forces in the x direction, and since two of them are already at an incline, it just makes sense for gravity to also have things in that x direction. Likewise, You got your forces in the y direction here. Now it looks like that's the only force, but of course there's a force that I'm missing because there's a support force keeping your box from falling through the ramp. It's got to be perpendicular to the surface. And can you see here that my y direction forces need to be parallel to each other? They can go in opposite directions, but they need to be in line with each other. So my positive y's are going to go this way, while my positive x's, again, I think it's best to do positive x's going down the ramp. It's okay if you don't do it that way. It's how I'm going to do it, though. And once I have that, then I need to go back to the equations that I'm dealing with. The sum of the forces in the x direction and the sum of the forces in the y direction. So we have actually a couple more forces than we're used to here, but that's okay. I'm not worried about it. I think you're going to be fine. So if I add these forces together, and remember, I can see, based on this being the positive, this is positive, this is positive, this is negative. I have f of f plus fgx minus f applied will equal the mass times the acceleration in the x direction. Here, in the y direction, this was positive, this was negative. I have Fn minus Fgy equals the mass times the acceleration in the y direction. And we're going to need to do some solving to plug things in. Here's where I do want to pay attention to some of the words here. First off, your acceleration in the y. How are you accelerating in this y direction? Hopefully you can see you're not, because you're going to be stuck to the ramp the whole time, so you can't be going up or down off the ramp in that y direction. So therefore, ay equals 0 meters per second squared. Second of all, now this constant velocity here is going to come into play, because that tells me, remember with constant velocities your acceleration is equal to 0, because you're not changing your speed, and acceleration by definition is how you're changing your speed. And I do assume when they say constant velocity, that does mean that you're going in a constant velocity up the ramp. Or down the ramp, doesn't really matter. But either way, it's in the x direction. So conveniently, that also equals 0. Now I've got different pieces I'm going to have to put together, different things I'm going to have to solve for. And I think it's best just to do them one at a time. And then see what I still have. And again, my goal is mu, which is not in my equations yet, but I think you remember where it goes. So, first thing I'm going to do is let's take care of the triangle. 200, like I said earlier, the 30 degrees from the ramp is what goes right here. I've got an FGY, FGX. Ignore those negatives that I put in for a minute. I only did that to show you on these equations down here what would be positive, what would be negative. I don't actually want them anywhere else. I don't want them in what I'm using here. Alright, so I want to solve each of these. So my adjacent side, my cosine of my angle, let's go ahead and just plug the angle in. Cosine of my 30 degrees is going to be my adjacent side over my hypotenuse. The sine of my angle will be the opposite side over my hypotenuse. And if I solve each of them like an ogre, get rid of the 200 on the one side. Remember, anything up that's, if you multiply a number upstairs and downstairs, they cancel. And if you do it on one side, you've got to do it on the other. Same trick here and here. So my FGY equals 200 cosine 30 degrees. My FGX equals 200 times the cosine, oops, not the cosine, times the sine of 30 degrees. So that's just a number. Let's find where I put my Desmos. Check what that number is. 200 cosine of 30. I'm getting that equals 173.2 newtons. And 200 times the sine of 30. I get that equals 100 newtons. So now I have here and I have here. I know I have the applied force because that was the 200. It looks like I just have these two things to solve for, which will not be too bad. I'm going to bring it over here. Remember, the force of friction is the same thing as mu times the normal force, which is where, remember, we get the mu from. We want to solve for mu, ultimately. But I'm going to need to know the normal force first. I'm going to go ahead and plug in this mu times the normal force and plug in the numbers I know so far. We have plus 100 minus 200 equals 0. Here we have Fn minus FGY was 173.2. That also equals 0. And I can use that to solve for my normal force. And once I have that, I can take it, plug it into my top equation, and I'm practically done. Mu times 173.2 plus 100 minus 200 equals 0. Combining like terms, these two are like terms. The mu term is not because it's got a coefficient, or it's got the variable with it. So I get 173.2 mu minus 100. Then I start solving it like an ogre after I collect the like terms. I get 173.2 mu equals 100. I'm going to then divide by my next layer. And I get that mu is 100 divided by 173.2. I'm going to check that on my calculator, and you can check me too. I'm getting 0.577. I think the thousandths place usually is a pretty good place to go with that. Alright, so that's actually not a crazy amount of friction, but at the same time, a decent amount. It's a little bit rough. So, the sliding coefficient of friction between the box and the ramp would have to be 0.577. Okay, so for your homework, I'm only giving you a handful of problems. I think there were 4. I want you to give them a try. They're going to look like various levels of what we just did. If you have a question, please let me know. And yeah, just notify me as quickly as you can. Don't put it off until Friday at midnight.